One of the key elements of many process plants is a distillation system. It's important for operators to understand how distillation systems work because it's part of their job to make sure the systems run properly. The purpose of any distillation system is to separate a liquid mixture into two or more components. The separation takes place in a distillation column or tower. The liquid mixture is called feed or charge, and the components into which it's separated are called cuts or fractions. Let's take a look at a simplified representation of a distillation system. In this example, the feed is stored in a tank. During operation, a pump is used to move the feed from the tank to a preheater. In the preheater, the mixture is heated under pressure to just below its boiling point. The pressure in the tower is lower than the pressure in the preheater. So when the feed enters the tower, it starts to boil. The vapors from the boiling liquid, which primarily contain the lighter components in the feed, rise in the tower. The remaining liquid, which consists primarily of the heavier components in the feed, moves down the tower and collects at the bottom. Some of this liquid is drawn off as the bottom's product, and some of it's routed to a device called a reboiler, which is connected to the bottom of the tower. The reboiler is usually a heat exchanger that's designed to vaporize the lighter components that remain in the liquid from the bottom of the tower. Vapors from the reboiler, or in some cases a mixture of vapors and liquid, re-enter the tower. The vapors then rise up in the tower. These vapors and the heat they contain are often referred to as boil-up. The hot boil-up provides heat that's needed for the distillation process to take place in the tower. The vapors that rise up in the tower are routed to a condenser. The purpose of the condenser is to cool and condense the vapors into liquid. From the condenser, the liquid flows into a receiver or accumulator. The receiver provides a reservoir for the liquid. Part of the liquid from the receiver is pumped back into the top of the tower, and part of it is drawn off as the tower's overhead product. Well, we've just looked at one simple example of a distillation system. Not all distillation systems are the same, but most of them have the basic equipment that we've just seen. At the heart of a distillation system is the distillation tower. Basically, a distillation tower is a series of distillation processes, or stills, stacked on top of each other. The process of distillation is sometimes referred to as fractional distillation or fractionation, and distillation towers are sometimes called fractionators. Fractionation is distillation that occurs at different levels in a tower. This is a simplified illustration of the inside of one type of distillation tower. This tower uses trays called sieve trays to separate vapors and liquid. The trays are spaced throughout the tower. They're called sieve trays because they have many openings in them, like a sieve. Here's a closer view of some of the trays. We've exaggerated the size of the openings to make them easier to see. The openings in the trays allow vapors to rise through the trays on their way up the tower. Each tray is also designed to hold liquid. Dams or weirs on each tray allow liquid to build up on the tray. Liquid that overflows the weirs flows into downcomers. The downcomers channel the liquid from tray to tray down the tower. When the upward moving vapors and the downward flowing liquid come in contact on each tray, the vapors transfer some of their heat to the liquid. Two things happen. The heavier components of the vapors become cooler and condense into liquid, and the lighter components of the liquid boil. The vapors then rise toward the next tray. As this process continues, the rising vapors contain a higher concentration of lighter components and a lower concentration of heavier components. So this is how the distillation process is repeated on each tray as the vapors rise through the tower. Now, not every distillation tower is designed in the exact same way. However, every tower can be divided into three basic sections. The middle section is where the feed enters the tower and part of the feed vaporizes. This vaporization is commonly known as flashing. So this section of the tower is often called the flash zone. The section above the flash zone is called the rectification section. In this part of the tower, the concentration of lighter components increases. The section of the tower below the flash zone is called the stripping section. In this section, the lighter components are vaporized or stripped from the heavier liquid. If a distillation tower worked perfectly, it would produce pure products. Unfortunately, that's not the case. The lighter products usually contain some heavier fractions, and the heavier products usually contain some lighter fractions. This is sometimes referred to as overlap. Distillation systems use several methods to help maximize the purity of the products. One of these methods is called refluxing. The vapors coming off the top of the tower are condensed in a condenser and then collected in a receiver. Part of the liquid from the receiver is sent to storage or to other units in the plant as the tower's overhead product. The rest of the liquid is pumped back into the top of the tower. The liquid that's reintroduced into the tower is called external reflux. Because it consists of liquid that was cooled in the condenser, the external reflux is cooler than the liquid in the top of the tower. As the external reflux cools the top of the tower, vapors made of heavier fractions condense. The liquid made of heavier fractions flows down the tower and is referred to as internal reflux. Meanwhile, the top of the tower is still hot enough to keep the lighter fractions in vapor form. The vapors are drawn off the top of the tower and into the condenser. Refluxing increases the purity of the overhead product because condensing the vapors made of heavier fractions keeps them out of the stream of vapors that leaves the top of the tower. Another method used to maximize product purity is called reboiling. The bottom's liquid that's drawn off from the tower is sent to a heater called a reboiler. The rest of the bottom's liquid is sent to storage or to other units in the plant as the tower's bottom's product. The reboiler heats the liquid it receives so that a mixture of vapors and liquid is formed. Depending on the system, either vapors or the mixture of vapors and liquid is then reintroduced into the tower. The hot vapors cause any lighter fractions in the liquid at the bottom to vaporize and move up the tower. This reduces the amount of lighter fractions in the bottom's product. The reboiler provides the major portion of the heat that's required to make the distillation process work. In the type of system we've been discussing, the heat supplied by preheating the feed is not sufficient for proper distillation. The reboiler is needed to provide enough additional heat to vaporize the lighter fractions in the tower so that the products meet specifications. Although all distillation towers serve the same basic function, they don't all have the same internal components. One type of tower uses trays called sieve trays to separate vapors and liquid. That type of tower is covered in the tower operation part of this program. In this part, we'll look inside two other types of distillation towers and see how their internal components differ. Let's start with a tower that uses trays with bubble caps. The holes in each tray are covered with caps called bubble caps. The slots in these bubble caps disperse the rising vapors through the liquid on the tray. Each bubble cap has many slots, and each tray has many bubble caps to spread out the vapors. This ensures maximum contact between vapors and liquid so that maximum heat transfer can take place. Another type of tower, called a packed tower, contains layers of devices called packing instead of trays with bubble caps. There are many different types of packing. Some towers have sections that are filled with cylindrical rings like the one illustrated here. It's known as a Raschig ring. Another type of packing is known as a burl saddle. The packing breaks up the liquid so that it flows over a large amount of surface area. This exposes more of the liquid to the vapors and increases heat transfer from the vapors to the liquid. Packing can be made from many different materials, including porcelain, copper, aluminum, and iron. The main requirement is that the material must be compatible with the liquid in the tower and the conditions under which the tower is operated. This is a section of another type of packing from a distillation tower. It's called a packing grid. Each layer in the grid has spaces for vapors to rise through the packing on their way up the tower. Liquid flows over these surfaces, which channel the liquid as it flows down the tower. The packing grid provides a great deal of surface area where contact between the vapors and the liquid can take place, so heat transfer is maximized. Some of this liquid is drawn off as the bottom's product, and some of it's routed to a device called a reboiler, which is connected to the bottom of the tower. The reboiler is usually a heat exchanger that's designed to vaporize the lighter components that remain in the liquid from the bottom of the tower. Vapors from the reboiler, or in some cases a mixture of vapors and liquid, re-enter the tower. The vapors then rise up in the tower. These vapors and the heat they contain are often referred to as boil-up. Temperature control is crucial to the operation of a distillation system. Correct temperatures are necessary to vaporize the lighter components of a liquid mixture while keeping the heavier components in the vapors to a minimum. If the temperatures at certain points in the system are either too high or too low, acceptable products won't be produced. Let's go over several points in a distillation system where temperature is monitored. As we do, keep in mind that the mixture we'll be referring to is a binary liquid mixture. That is, a mixture that has two components. We'll begin with the temperature at the top of the tower. The temperature at the top of the tower should be at or slightly above the boiling temperature of the desired overhead product at the operating pressure of the tower. If the temperature at the top of the tower is higher than it should be, more of the heavier components will vaporize and become part of the overhead product, instead of flowing down the tower as a liquid. On the other hand, if the temperature at the top of the tower is lower than it should be, less of the lighter components will vaporize. Some of the lighter components will remain as a liquid and flow down the tower. The temperature at the bottom of the tower is also important. The temperature at the bottom of the tower is usually slightly below the boiling point of the heavier component. If the temperature at the bottom of the tower is too high, more of the heavier components will vaporize and move up the tower instead of remaining as a liquid. If the temperature at the bottom of the tower is too low, less of the lighter components will vaporize and move up the tower. Another place where temperature control is important is at the feed point. The temperature at the feed point should be within the boiling range of the mixture. The temperature at the feed point should be close to the temperature of the feed tray. The temperature of the feed tray depends on its physical location in the tower. For example, the lower the feed tray is in the tower, the higher its temperature will be. If the temperature at the feed point is higher than it should be, more of the heavier components will vaporize and move up the tower instead of moving down the tower as a liquid. On the other hand, if the feed point temperature is too low, less of the lighter components will vaporize, and more lighter components will end up in the bottom of the tower. While the temperatures at various points in a distillation system are important, the relationships between the temperatures are also important. The temperature decreases as the material moves higher in the tower. The gradual decrease in temperature from the bottom of a distillation tower to the top is called the temperature gradient. The temperature gradient is measured in terms of the difference between the temperature at the bottom of the tower and the temperature at the top of the tower. In order to maintain the proper temperature gradient, temperatures at critical points in the system must be controlled. Temperatures in a distillation system are typically controlled in three ways. One way is to control the temperature of the feed mixture by using a preheater. This regulates the temperature at the feed point. At the bottom of the tower, temperature is controlled by the amount of heat that is added by the reboiler. This added heat is referred to as boil-up. The temperature at the top of the tower is controlled by the amount or the temperature of the cool liquid that's pumped back into the tower from the overhead receiver. This is called the reflux rate. Increasing the reflux rate decreases the temperature at the top of the tower. Some distillation systems contain equipment known as pump-arounds. The purpose of a pump-around is to remove hot liquid from the tower and pump it through a cooler. The cooled liquid is then reintroduced at a higher level in the tower. A pump-around helps control the temperature of the internal reflux. Since pressure affects the boiling temperature of a liquid, it's an important factor in the distillation process. If pressures in a distillation system are not correct, product purity could decrease. Tower pressure is often controlled by a pressure control valve located on the overhead receiver. This valve controls pressure by releasing vapors and any non-condensable gases that have collected in the receiver. In some cases, a vacuum system draws gases from the receiver to control tower pressure. Another pressure that's important to an operator is the tower's differential pressure. The tower's differential pressure is the difference between the pressure at the bottom of the tower and the pressure at the top of the tower. This difference in pressure is caused by the flow of vapors in the tower. Without vapor flow, there is no differential pressure. Generally, If the rate at which the vapors move up the tower decreases, the differential pressure will also decrease. And if the rate at which the vapors move up the tower increases, the differential pressure will increase. Changes in the differential pressure may indicate that a problem exists. For example, an increase in differential pressure could be an indication that the feed rate is too high. Too much feed entering the tower will overload it. If this happens, the differential pressure will increase, and the tower will be unable to make the desired separation. In this case, it might be necessary to decrease the feed rate. Now, changes in the tower's differential pressure may be caused by other problems. For example, if the differential pressure increases, the boil-up rate may be too high. In other words, the reboiler may be returning too much vapor or vapor-liquid mixture to the tower. This problem can be corrected by reducing the boil-up rate. Another problem that may affect the tower's differential pressure is a decrease in condenser efficiency. If the condenser's tubes are plugged or there's not enough cooling water flowing through the condenser's pressure will increase. As a result, the flow of vapors from the tower to the condenser will decrease, and so will the vapor flow up the tower. This means that the tower top pressure will increase, and the differential pressure will decrease. If a condenser problem is suspected, the condenser should be checked, and corrective action should be taken if necessary. Now, changes in the tower's differential pressure may have other causes in addition to the ones we've identified. So it's important to carefully evaluate any situation before corrective action is taken. In this topic, we looked at two key factors in the distillation process: temperature and pressure. Remember that although we discussed them separately, temperature and pressure work together. Both of these factors must be correct for the distillation process to work properly. Now, try to answer some practice questions to check your understanding of what we've gone over.